Have you ever wondered how complex data can be visualized in a simpler form? Or perhaps how we can make sense of massive amounts of information that might seem perplexing at first glance? Enter the world of self-organizing maps, or SOMs for short. SOMs serve as an ingenious solution to the challenge of visualizing high-dimensional data, transforming it into a lower-dimensional grid, making it easier to digest and understand. This process is called dimensionality reduction, and it's just one of the many applications of SOMs. Imagine a grid of nodes or neurons, each representing a specific location in a lower dimensional space. This grid forms the basic structure of a SOM. Each neuron is associated with a weight vector, which is initialized with random values or drawn from the input data. Now, during the training phase, SOMs employ a method called competitive learning. Here, all the neurons compete to be the best match for the input data. The neuron whose weight vector is most similar to the input data wins this competition and is called the best matching unit, or BMU. But what makes SOMs truly remarkable is their ability to preserve the topological relationships in the input data. This means that neurons that are spatially close in the grid respond to similar types of input data. This feature allows SOMs to maintain the structure of the data, keeping similar data points close together on the grid. After the BMU is identified, the weight vectors of the BMU and its neighboring neurons are updated. The closer the neuron is to the BMU, the more it's updated. This process encourages the neurons to adapt their weights to better represent the input data, resulting in a self-organizing map. The training process is iterative, meaning the same data may be presented to the network multiple times, allowing the SOM to gradually fine-tune its representation to the input data. Now, let's talk about the applications of SOMs. They are used for data clustering, grouping similar data points together on the grid. This makes SOMs a valuable tool for exploratory data analysis. SOMs also help in visualizing and understanding complex high-dimensional data sets. By mapping data onto a two-dimensional grid, patterns, relationships, and outliers become easier to see. They are used for tasks like image recognition, where they can learn to recognize patterns or features in images. Additionally, they can identify anomalies or outliers in data, making them useful for anomaly detection. SOMs can also be used to build recommendation systems by identifying clusters of users or products with similar characteristics. In the realm of marketing, they help segment customers into groups with similar preferences, enabling targeted advertising and product recommendations. So the next time you're confronted with a complex, high-dimensional data set, think about how a self-organizing map could help simplify your task. Whether it's clustering data, reducing dimensions, visualizing data, recognizing patterns, detecting anomalies, or building recommendation systems, SOMs have got you covered.